All right, so X-ray interactions within the patient. We're going to need to learn 3 ways the X-ray beam can interact, the X-ray photons can interact with the patient's body. And that's one important thing to understand first, is that the X-ray beam, what we call the primary beam, is made of many, many small individual X-ray photons, right? Each X-ray photon has its own individual energy, and each photon interacts one at a time with an atom. So these are single photons interacting with single atoms, but there's a collective, accumulated effect of all of these interactions that produce our image. So let's start here. All visibility characteristics of the latent image, we'll need to make sure we understand what latent image means, but all visibility characteristics of the latent image reaching the image receptor are controlled by the relationships of the set electrical techniques, electrical variables, to the atoms that make up the tissues. So how the X-ray beam interacts with the tissue. You change the X-ray beam by changing the electrical settings, right? What were our main electrical settings that we change? There's 2. KVP and MAS, right? Or let's make sure we separate out the S, right? So KVP and MA, right? But time is there. It's just not an electrical setting. But so the settings that we make affect the energy and quantity of the X-ray beam, and those changes change the interactions with the tissue. That's the idea. 3 types of interactions with the X-ray beam, X-ray photons, and the atoms that are making up the patient. We call them the photoelectric interaction, the Compton interaction, and coherent scattering, or also called classical scattering. Classical or coherent scattering has 2 flavors. They are referred to as Thomson and Rayleigh interactions. So we'll go through from top to bottom on this list here. So consider this atom. It's a happy atom. It's neutrally charged, no electrical charge. It's sitting there minding its own business. Okay, maybe it's an atom. Well, what is it actually? 4 to 10. So it's an atom heavier than oxygen. It's 10 on the table. You can tell me what 10 on the table is if you want. But it's an atom in the patient's body. Okay. By the way, most of your atoms are either hydrogen or oxygen. Okay, you also have a bunch of other stuff too, but hydrogen or oxygen makes up the majority of your body. So consider if this were like an oxygen atom in your body. Okay, a X-ray photon comes in from the X-ray tube, came from the focal spot, comes down, doesn't interact much with the air in the room, and then hits some part of the patient. Okay. If this X-ray photon is low enough in its energy, so it's high enough in energy to kick out an electron, but low enough in its energy to where it's completely absorbed, we're going to call this a photoelectric interaction, the photoelectric effect. This effect was discovered in 1905, and this is what Einstein won his Nobel Prize for. He discovered the photoelectric effect, the fact that light can eject electrons from atoms, right? The exact opposite we've already learned, right? We've learned that electrons can emit a photon. In this case, a photon is absorbed into an electron. So this electron shown here called a photoelectron, that was sitting where my laser pointer is right now, minding its own business. Okay? An X-ray photon comes in and dumps all of its energy into it. Okay? Now the electron has gained energy. Okay? When electrons gain energy in an atom, they have to move up a shell level. Okay? If an electron gains enough energy, it moves up and just out of the atom. Okay? And is ejected from the atom. For this to happen, the entire photon's energy has to be absorbed into that electron. Okay? Once that happens, the electron gets ejected from the atom. The electron is gone from the atom. It's gone now. But importantly for this interaction, so is the photon. The photon, the X-ray photon, gets absorbed by the electron and is no more. It's gone now. Okay? So complete absorption of the X-ray photon by an orbiting electron, no secondary X-rays are left over. The X-ray photon is gone. Okay? This is most likely to occur in the innermost shells of atoms, less likely to occur in the outermost shells. Can you guys tell me why? Why is it more likely to occur in an inner shell of an atom versus the outer electron shells? The inner shells are bound more tightly. They're pulled on more tightly. Recall we talked about centripetal force, right? The closer you were to the center of the nucleus of an atom, the more tightly bound to that atom you are, okay? It is easy to eject an outer orbiting electron and harder to eject one of the inner shell electrons, okay? So think about if this were an outer shell. Think about this happened in the outermost shell. The X-ray photon would put its energy into the electron would go out, you get ejected too, but there would be leftover energy, okay? There would be leftover energy because it didn't take that much energy to eject an outer shell electron. However, with an inner shell electron that's being bound more tightly to the atom, it takes more energy to make this happen, and it's more likely that the X-ray photon's energy will be completely absorbed, no leftover X-ray photon, in order to eject the orbiting electron. So it's more likely in the innermost shells of atoms. This happens because the X-ray photon carries potential energy. That energy is deposited into the electron, giving the electron kinetic energy, and ejecting it. The word photoelectron means an electron which has captured a photon and is now traveling fast. Because the atom in question has lost an electron, we say the atom has been ionized. This fact that an X-ray photon can ionize an atom, can eject electrons from atoms, means that X-rays can change the shape and structure of molecules, potentially causing harm to the living thing. Now, if this happens to the electrons in the atoms of this table, no big deal, right? Because the electrons in the atoms of this table, everything's pretty much stationary, stable, not changing, right? But the electrons in your atoms are forming bonds with other atoms to make molecules. For example, your DNA is a molecule, right? And if we remove some electrons from your atoms, that will change the bonds between atoms, potentially changing the shape of molecules like your DNA, okay? Your DNA gives you the instructions to make you, and if we change those instructions, we make different things than the normal stuff, right? This is why X-rays are harmful. So to be very clear, X-rays are harmful because they can ionize matter. Ionizing matter means taking an X-ray photon, using it to kick out an electron from an atom. The atom is now ionized. The atom has a net positive charge. So if you didn't catch that, a happy atom has no electric charge. It has negative charges and positive charges, but they equal, making zero charge. If you remove a negative charge, negative electron gets removed, the atom left behind now has a positive charge. It will interact differently than it did when it was neutrally charged, making a different interaction, potentially making some biological changes. And importantly, this electron leaves the atom. The electron is also electrically charged. It has a negative electric charge. So that electron may go now and have some interaction with some atom nearby, and if it's traveling fast enough, can have either a Bremse or characteristic interaction with an atom nearby. Remember the interactions in the X-ray tube were interactions of electrons with atoms, right? Well, there is an electron that's now moving fast inside the patient's body. It won't make it to the image receptor, but it can cause some havoc somewhere else in the patient's body, nearby, but somewhere else in an atom nearby. So this is important. The atom is ionized when the photoelectric effect happens. And importantly, this photoelectron cannot reach the image receptor. The X-ray photon has been absorbed. The electron that absorbed it can't get to the image receptor and expose the receptor. So what happens here is the latent image, the image left on the image receptor before it's processed, is now going to have a microscopic spot with no exposure. Unexposed or white area. The photoelectric effect accounts for all of the white areas on your image receptor. Now there's a integrated cumulative effect of all of these photoelectric interactions producing shades of gray. We get our whites from the photoelectric interaction though. In the final image, the resulting gray level of a particular tissue is primarily due to the accumulation of these unexposed areas as a proportion of all of the interactions. So some of the tissue interactions are photoelectric. Those account for the white stuff. Okay, the white parts of the image. So there are more photoelectric interactions in bone than there are in, gas in the body, right? Because the bone is denser. The photoelectric effect allows us to produce subject contrast in the latent image carried by the remnant beam, and we can't make X-rays without subject contrast. The subject of the next chapter is subject contrast. Who knows if we're actually going to make it there today, but we'll try. So we can't produce an X-ray if we don't have shades of gray, and the white part of the shades of gray comes from the photoelectric interaction. Now here's when this happens, okay? This can only occur, we can only call it a photoelectric interaction if the photon is entirely absorbed, okay? The photon can only be entirely absorbed if its energy is only slightly higher than the binding energy of the electron it interacts with. Also recall that there is nothing attracting that photon to that specific electron. This is just chance, okay? Sometimes it does, sometimes it doesn't. Many atoms and many photons means that sometimes those photons are going to interact directly with an electron. Unlike charged particles, which can be attracted or repelled from each other, you know now that X-ray photons, or at least you will know now, that X-ray photons don't have any electric charge. They are not pushed or pulled toward anything. They just travel in a direction, okay? They travel in a straight line at the speed of light, and they carry energy. That's all that they do, okay? They're not pushed or pulled from anything, and they don't do anything until they absorb or interact with another piece of matter, like an electron. This is just a chance interaction. If an X-ray photon has energy well in excess of the binding energy of the electron that it interacts with, then the interaction is not going to be a photoelectric interaction. It'll be one of the others. A Compton interaction is what it will be. X-rays in excess of the binding energy of the shell are converted into the speed of the electron. Let's give it just a quick example. Let's just make up some toy model example. Let's say this photon had, it had an energy of 60 keV, okay? Let's say the binding energy for that electron was 20 keV, okay? No, I don't like that. Let's say it was, because it has to be close. Let's say it was 57 keV. It's kind of like tungsten, right? This X-ray photon of 60 kiloelectron volts interacts with an electron that is held into the atom with 57 or negative 57 kiloelectron volts. So it takes at least an energy of 57 kiloelectron volts to just remove it, okay? If this X-ray photon had exactly 57 keV, then we would eject the electron, but the electron would be ejected with nearly no speed. It'd be moving at basically zero, okay? But it would be out of the atom, okay? If this X-ray photon has 60 keV, for example, now the X-ray is absorbed into the electron. The photoelectron leaves with an energy of 3 keV. That's how much energy it has. We can say that's the kinetic energy of the electron, and you can convert that through various ways into a velocity, which we don't need to. But in principle, that energy now can tell you how fast the electron is, okay? How much momentum it has, mass and velocity. So that's what's left over, 3 keV because incoming photon had 60, it took 57 to remove the electron, so the leftover product is 3, and that's how much energy that thing is moving with. If, for example, we now had a photon coming in with 67 keV, right? Then now the photoelectron leaves with 10 keV worth of energy. There's a conservation of energy, okay? So it's an easy thing to talk about. You can know, they may tell you what the binding energy for the electron was and what the energy for the incoming photon is, and from that you can work out how much energy the photoelectron leaves with. Okay. The likelihood of this interaction goes down as the energy of the X-ray beam goes up. What setting changes energy of the X-ray beam? KVP, right? So as you raise KVP, we make less and less photoelectric interactions, which explains why your images get darker and darker and darker as you increase KVP, because you're making less and less photoelectric interactions, and those account for the white parts of your image. Images where we want a lot of black and white, high contrast, we use low kilovoltage settings to allow for more photoelectric interactions. Images like of the chest, where we just want dark and shades of gray, use high kilovoltage, so there's less of the photoelectric interaction happening. Photoelectric effect cannot occur if the photon's incoming energy has less energy than the electron's binding energy. So let's go back to this picture. If this if this electron were here, and it were bound with, let's use the same thing, negative 57 keV, we're just making a number up, and this incoming photon had 56. Again, the negatives almost don't matter, so let me just get rid of the negative, okay? If this incoming photon had 56 keV, it doesn't have enough energy to eject the electron, okay? It might temporarily push the electron up to an outer shell, okay? The electron can absorb that much energy, but it isn't enough to eject the electron from the atom. The electron will temporarily absorb that energy from the photon. It will raise up a shell level, let's say, and then almost immediately it'll jump back down to here and re-emit that photon out in a randomly different direction, and that photon is going to have the same energy that the incoming photon had. An electron can temporarily absorb an electron can temporarily absorb a photon, raise up a little bit, and then immediately jump back down and re-emit the photon. By the way, that's what glow-in-the-dark things do. They absorb the light in the room. The electrons in the matter of the glow-in-the-dark object raise up a couple shell levels, and then you take it away from the light source, and they all drop back down. The electrons drop back down to their lower shell levels, re-emitting the light, and you see the thing glow. Okay. This interaction that I just described is the last interaction we'll describe, the classical or coherent scattering interactions. It's the last one we'll get to. But anyways, photoelectric interactions can only happen if the incoming photon's energy is higher than the binding energy of the electron, but only a little higher. Okay? If it's a lot higher, a different interaction happens, Compton interactions. And if it's lower than this energy, classical scatter or coherent scatter happens. Okay, so photoelectric effect is a very specific effect producing the white on the image, and it can only happen when the X-ray photon's energy is close to, a little bit more, but close to the binding energy for the electron. Okay, let's move forward. So let's take a look. This table is kind of nice. I don't think I include this table in the lecture notes because when I convert the PowerPoint to lecture notes, I can't convert pictures. I can only convert the words. So this you'll have in the text, you'll have in the PowerPoint notes that I sent you, but you won't have in the printed out notes. Anyways, what this table shows you are, on the left column, here are some atoms of stuff that you'll find in the body. carbon, oxygen, calcium, iodine, barium, tungsten, lead. Maybe not all of these in the body necessarily, but in and around the body, in and around the X-ray room, these are things. Now, each column gives you a shell. Okay, K shell is the innermost shell of an atom. L shell is the second shell out. M, N, and O as we go out and out and out. So look at, here's tungsten. We learned tungsten earlier, right? Tungsten we learned about for target interactions. The K shell for tungsten, the innermost shell for tungsten, is held in, the electrons are held tightly, at negative 69 keV. If you were an X-ray photon traveling toward a tungsten atom, and you wanted to remove the K shell electron from tungsten, how much energy do you need to have?
Slightly higher, right?
Yeah, at least that much or slightly higher, right? So what's the minimum amount of energy you need to eject the K shell electron from tungsten?
69.
69 keV. Why not negative 69 keV? Because the negatives don't matter, because X-ray photons don't have electric charge, and negative doesn't mean a lack of something. Negative just means the opposite of positive, right? It's hard, maybe, you guys are doing really well with this, but it can be hard for people to stop paying attention to the negative because it doesn't matter here. It's not a negative, it's just it's a different kind of energy. Because it's different than positive energy. So here's the trick, okay? In electromagnetism, an electron like this, okay, we label as an E with a little negative, okay? It has an electric field around it. It interacts with the electric field. It has electric charge that's sort of built into the electron, right? The electric field originates at infinity and points toward the electron.
So it just has a negative energy charge.
It has an opposite charge to a proton. So protons, as a little elementary particle, they have an electric charge, which is exactly the opposite. So electric fields have a magnitude and a direction that they point in, okay? Electrons' electric field always points towards it, okay? A proton's electric field, you probably guessed it by now, always points away from it, okay? These field lines extend to infinity, but they point away from the object, okay? This is the difference between electrons and protons. They're different in mass, but as far as electric charge, they both interact with the electric field. It's just that with an electron, the electric field points toward the electron, and when a proton, the electric field points away from the proton. Okay, so negative doesn't mean you have less of something in this case. It just means you have the opposite type of thing. Okay, they use negative and positive. They could have used, I don't know, A and B or if they wanted, right? But they use negative and positive because it works better in the mathematics. So, anyways, for our purposes, we don't have to worry about the negatives because X-ray photons have zero electric charge. Okay, they're not electrically charged at all. Okay, so take a look. Move up the chart here. Notice oxygen. You're made of a lot of oxygen. They don't include hydrogen on here, but you're made of a lot of oxygen. It's one of the most abundant molecules in your body. And its K shell is only held in place with 0.5 keV, right? Negative 0.5, but 0.5, right? It takes much less energy to eject the K shell of oxygen than it does to eject the K shell of tungsten. Why? Because tungsten's a much larger molecule. The positive charges in the nucleus of tungsten, there are more of them. So it's holding on to each of its electrons a little tighter. Okay? Oxygen being a smaller molecule, only having 8 protons in the nucleus, it holds on to its orbiting electrons less. So it's easier to eject them.
Because we have to have a vacuum, otherwise you would have a lot of interactions with oxygen.
Yeah, exactly right.
So you build up pressure.
And so you would have a lot of interactions, meaning the electrons in the X-ray tube wouldn't be able to get from cathode to anode without running into a ton of oxygen molecules and ionizing all of them, right? And dumping all the energy in all different directions, right? And then you might get damage to the cathode, right? But importantly, you wouldn't make X-rays, right? You might make some, but way less and be way harder to gauge how many you're producing. So we need the vacuum in the X-ray tube. Yeah, you're very good, very good. So let's take a note here. We're going to need to know this one for this next idea. So Good. Pay attention to iodine and the L shell for iodine. Negative 5 kV. That means you need at least 5 kV worth of energy to eject the L shell of iodine. So this next question here says, within a patient's body, during some procedure, they call it an IVU, intravenous urogram, okay? A 30 kV X-ray photon undergoes a photoelectric interaction with the L shell of iodine. What will be the kinetic energy of the photon, or the photoelectron speeding away from the atom? What do you need to know? You need to know the binding energy for the L shell of iodine, negative 5, and you need to know the X-ray photon's energy, right? So we have the X-ray photon, 30 kV. The L shell for iodine is negative 5 kV, okay? Again, you can ignore the negative. So 30 minus 5 equals 25 kV. The photoelectron produced from this interaction has an energy of 25 kiloelectron volts. It took 5 of the X-ray photon had 30 to give, 30 kV to give, okay? It took 5 of its 5 kV of its energy just to get the electron out of the L shell of iodine. And so what's going to be left over is a photoelectron with 25 kV. The electron absorbs all of the photon, but it only used 5 kV to get out of the atom, so it's going to retain the other 25 kV. The photoelectron leaves with 25 kV. And that's what's shown here. 30 kV of the incoming photon, 5 kV in binding energy, takes 25 kV, or leaves behind 25 kV. The ejected photoelectron has 25 kV of kinetic energy. We got used to expressing kinetic energy in joules, right? In the previous class. I'm not going to teach it because it's not important, but there's a way to convert from kV to joules. Okay, I'm not going to worry about that right now. So saying that the kinetic energy is 25 kV would be equivalent to expressing it in a unit of joules too. They're both interchangeable. So that's the photoelectric effect. Remember, the photoelectric effect produces a white spot on the image. So here's the important notes from photoelectric. Produces a white spot on the image, ionizes the atom, and the number of these interactions decreases drastically as kV goes up. White spot on the image, ionized atom, less interactions with higher kV. The next interaction is the Compton interaction. Compton is the name of the scientist. Where photoelectric is the name of the thing that happens, Compton is the name of the scientist. Okay. Compton interactions are similar, right? Some of the X-ray photon gets absorbed into the electron, ejecting the electron. But the important part about a Compton interaction is we have a leftover secondary scattered photon that can reach the image receptor. So it is partial absorption of the X-ray photon's energy. This creates secondary radiation. So here's an important note. It's really important for learning about X-rays. X-ray photons, all photons of light in X-ray, are defined by their energy. We express energy in units of kilovolts. Okay? So if you see a photon incoming, let's say 80 kV like this one has incoming from the top, and you see another photon coming out from the bottom at 78 kV, it's not the same photon with less energy, it's a new photon. So it's secondary. Remember, X-rays travel in straight lines. So you see an X-ray photon traveling in a different direction with a different energy, it's a different photon. Secondary radiation is emitted which is scattered in a different direction than the original photon. Exactly what direction is a harder thing to talk about, so we don't in radiography. It's just a different direction. It's scattered. This is most likely to occur in the outer shells. Why in the outer shells? Because of less binding energy in the outer shells. It's easy to eject the outer shells. So yeah, 3 things here. Incoming photon, recoil or ejected electron, and secondary radiation. Is the atom ionized after this interaction? Yeah, it's ionized and the electron got ejected. But importantly, we now still have a leftover photon. Okay? The recoil electron is ejected from the atom because we gave it increases in kinetic energy. The atom is ionized. The electron ejected from the atom cannot reach the image receptor, but the scattered X-ray photon can. Can you tell me what the binding energy for that electron had to be by knowing the incoming and outgoing energy? Sergio? 2 kV. That electron had to be bound with about 2 kV worth of energy. Okay, that is because that's all that was lost here, right? We came in with 80 kV from the top. The secondary photon scattered with 78 kV. We only lost 2 kV. That means that photon had to be bound with 2 kV worth of energy. This is the L shell of an atom, because it's the second shell out. So, in principle, you could go find and tell me what atom this is, right? Whatever atom has an L shell bound with 2 kV, go find that one and bring it back to me, right? I won't make you do that, because I don't know it. All right, so things to remember about Compton interactions. The likelihood of a Compton effect decreases as energy increases, but only slightly. And the Compton effect cannot occur if the incoming X-ray photon has less energy than the electron's binding energy. So if an X-ray photon came in with, 1.9 kV worth of energy, it probably wouldn't be an X-ray photon. But if it came in with 1.9 kV worth of energy to that previous atom, and that previous atom needed 2 kV to eject the electron, it won't do it. It will absorb the photon, the electron will, and then it will re-emit it. Back out in a different direction, same energy, but different direction. And because why not? We're going to have different names to remember here. So the Compton effect is the best name to remember, okay? However, it may also be called modified scattering and incoherent scattering. It's called incoherent scatter because because the secondary photon's energy is different than the incoming photon, so it's not coherent. We can't know ahead of time unless you tell me exactly what atom and what electron it's going to interact with. You can't tell me what the outgoing photon's energy is going to be. Incoherent. Anytime you see an outgoing photon that's traveling in a different direction and or has less energy than the original, it's a new photon. No matter what, okay? Different direction and or different energy. It means it's a new photon. We define them by the direction they travel in and the energy that they have. Different origin than the incoming photon. X-rays are identified by their energy as well as direction. Okay. So things to notice from that what we just talked about. in the interaction we gave let me just come briefly back to the picture here, and then I'll come back to this. In the interaction we just showed, an incoming photon of 80 keV ejects an electron from an atom, and then a secondary photon leaves with 78 keV. Okay? Notice that most of the photon's energy is retained in the new photon. 78 of 80, right? Most of the energy gets retained. And that's going to be an important note here, is that most of the energy is carried away by the scattered photon. With high energy, the scattered photon is likely to penetrate through the body and reach the image receptor. However, because of its random direction, scattered radiation is a form of noise, decreasing image quality because it raises noise in the signal-to-noise ratio idea. More noise, no more signal. And because it retained most of its energy, it could jam straight through the body, not touch anything else, hit the image receptor, scattered radiation still. However, there's lots of other atoms nearby. Okay? It is likely in a Compton interaction, for the first Compton interaction, producing a secondary photon, for that secondary photon to now go and make another Compton interaction, and another one, and another one. Okay? A series of Compton interactions may occur until the remaining energy is only slightly above the binding energy of that last atom, and then a photoelectric interaction takes place. Okay, so coming in from the right, you see a photon. Photon ejects electron here. Secondary photon continues on, interacts with the new atom, ejects the electron, loses energy and continues on. Ejects another electron, loses energy and carries on. But on this last interaction, we're saying that as it gets down to that low energy level, it'll reach a point where its energy is only a little bit higher than the binding energy for the electron it's about to interact with. Therefore, photoelectric interaction is what's likely, ending in another white spot on the image. Okay, so these can make it to the image receptor. These can go down this cascade of atomic interactions and eventually just be absorbed. Okay, or anything in between. Some of them get absorbed completely by interacting with several atoms. Some of them make it straight to the image receptor after interacting with only one or two atoms, and everything in between that. This is how we can produce scatter at these different energy levels. Okay, you might want to ask, let's go back to this image. You might want to ask, we say the secondary radiation, this is a previous image, secondary radiation is emitted and scattered in a direction different from the original. So you might want to ask, well, how can we go about telling how much of a deflection there is? Okay, and I can't give you an exact way to figure out how much deflection there is, but what I can tell you is scattered X-rays at higher energies are deflected less. Okay, at a lower energy, it is more likely to deflect at a greater angle. So they show incoming to the atom. It is more likely at high energies to deflect at lesser angles, and at low energies it's more likely to deflect at steeper angles, like back towards the original direction. Okay, and that's about the best I can give you for this. Yeah.
So, for example, if you had a pool table and you threw the main ball at the clump of the triangle.
Yeah, the racked balls. Yeah.
The racked balls. Then they would go in all different directions.
Yes. And if you shot that pool ball out of a cannon, right, assuming the pool balls all didn't blow up, more of them are likely to travel in the same direction that the pool ball was traveling in originally, right? But at a slower velocity, like where your cue stick hits the pool ball, they spread in all directions, right? Some of them even come kind of back towards you. right?
So,
Yeah.
okay, there's, what was it, that if the incoming electron hit it in such a way, then it would just disappear, it would just evaporate. I'm not sure what that was.
Are you talking about the Compton interaction or the?
I'm not sure which
Okay.
one that
So
applied to. I didn't understand it, so I was like, what?
Gotcha. So this Compton interaction, right? This is what we've been talking about for this, and what I'm getting at is the angle this photon scatters at, right? With high energy, the scattered photon travels more or less in the same direction as the original photon, and at low energies, the scattered photon is more likely to travel at an angle greater. Yeah. Okay. That's the only thing to take away is just there's a relationship between energy and the direction that the photons scatter in.
Okay, so on the Compton series,
yeah, this one.
Are we concerned with the math that each one of those? Do they even attempt to go, well, this is going to interact with?
No, you just. No, we don't care how many, all we care is that the important note from this is the reason why this is even possible is because with a Compton interaction, let's say the first one, right? The photon that leaves, the secondary photon, retained most of its energy, right? So because it retained most of its energy, it is likely that it will run into another atom and do this again, okay? And again and again and again, cascading until it loses all of its energy. Or it might go straight towards the image receptor and make it all the way through the body without interacting with the patient again, right? We're just saying that the note is that the scattered photon retains most of its energy, and it can do things with that energy now, interact with more atoms, or travel straight to the image receptor and expose the receptor, become part of the remnant beam.
The more energy, the more potential it has to interact.
Yeah. Yes, yeah, because that's what photons are. Photons are a form of potential energy. They don't do anything. They carry the potential to do something, but they don't do anything. Think of the photons traveling between the sun and here. They don't do anything. They just travel through space. They don't do anything until they interact with something, some matter, some electrons, right? And then they make those electrons move, right? Yeah.
So that's why we say that we want higher kV and lower.
Higher kV puts more of the photons into the remnant beam, getting us more signal to the receptor, more information in the remnant beam, yeah. But there is also a relationship between increasing kV and the number of scatter events that happen too. So those go up too. Scatter goes up as kV goes up. But yeah, you guys are doing great. This is good. Let's briefly go through a couple things. Let's just briefly compare and contrast Compton interactions versus photoelectric interactions, the two that we've covered so far. So, some things. Since photoelectric interactions produce the subject contrast in the signal of the remnant beam, and Compton interactions destroy that, remember Compton interactions are scatter, right? Compton interactions work in direct opposition to photoelectric interactions. Now, there has to be a balance. Compton interactions are what you typically think of as scatter, noise on the image receptor. Most of, 97% of scatter caused by Compton interactions. The rest of the scattering events come from this next one that we're going to talk about called coherent scatter. So when you're asked on a test or quiz, what type of interaction produces most scatter radiation, noise on the image? It's Compton interactions. Most of them, 97% come from Compton interactions. Compton interactions require that we interact with the outer shell of an atom and that the incoming photon have much higher energy than the binding energy for the electron in question. And we ionize the atom and we have a scattered photon. We don't care for image creation purposes. We don't care about the scattered electron. The ionized electron, the ionized atom, we don't care about that for the image. It matters for the patient. When we get to radiation safety, we're going to care a lot about that. But for image production, we care about the scattered photon. Okay, the next type of scatter is called coherent scatter. Coherent scatter is called coherent scatter because we know if you tell me a coherent scatter event happens and you tell me the incoming photon's energy, I can just tell you what the outgoing photon's energy is going to be because it's the same. Okay? And that's the point with coherent scatter. Coherent scatter is kind of like glow-in-the-dark stuff. Okay? Momentary absorption of a photon followed by almost immediate re-emission of that same energy photon, but it's new because it's going to travel in a different direction. So momentary absorption of the X-ray photon by an orbital electron or by the atom. This is your choice. They go by different names. The Thomson and Rayleigh interaction the two names are given because one deals with interaction with the electron and a photon, one deals with the interaction of the atom as a whole and a photon. They're effectively the same thing. If you take like the bird's eye view and stand outside of the atom, you have an incoming photon and an outgoing photon, no matter which of the two types of interactions happen, Thomson or Rayleigh. Secondary radiation gets emitted, scattered in a different direction from the original. The important thing for the patient here, the atom is not ionized. Because the atom is not ionized, you didn't make any physical changes to the structure of their body. The way that the atom is not ionized is because the incoming photon's energy has to be less than the binding energy for the electron. Here it is. Occurs when the energy of the incoming X-ray photon is less than the binding energy of a strongly bound orbiting electron. Do you think this interaction is more likely to occur in the inner shell of an atom or the outer shells? What do you think, Abby? You said something.
Maybe the outer shell?
Which inner shells or outer shells, which are more tightly bound? Inner shells. And we need the photon to have less energy than the binding energy, right? So with inner shells, the binding energy is higher, so it's more likely that an X-ray photon will have less energy than the binding energy. So it's more likely to occur in inner shells, but it can occur anywhere. It's just more likely to occur in the inner shells. Takes more energy to remove an inner shell, so it's more likely that a photon will have less energy than the inner shell's binding energy than it will for the outer shell's binding energies. The orbiting electron gets momentarily raised to an excited state, but not so excited that it leaves the atom. It's not ejected from the atom. The atom is not ionized. That electron raises up to a higher shell and then immediately jumps back down because we didn't give it enough energy to get out. Okay, it's kind of like, you take a cannonball, right, and you fire it up at the sky, right, with enough energy, I can fire it far enough to get it out of the Earth's atmosphere, right, and make it orbit around the Earth, right, if I give it enough energy. But anything less than that, it's going to go up and then back down towards Earth, right? When it hits Earth, it's going to make a boom and make some sound, right? In this case, the photon gets absorbed in the electron jumps up, but not high enough to get out of the atom, not high enough for the cannonball to get out of Earth's gravitational field. So it's recaptured by the atom, causing it to shoot out the photon that it had absorbed. The photon goes in a new direction, so it's scattered radiation, but it's coherent scatter because we know what the energy will be for that photon. It'll be the same as the incoming energy. It's called a scattered photon because it's traveling in a different direction. Because it's traveling in a different direction, it has to be a new photon. It cannot be the same as the original. You can picture this as a photon interacting with a single electron, the electron absorbing and then re-emitting a photon of the same energy, called Thomson, or you can picture an entire atom absorbing a photon and then immediately re-emitting a same energy photon in a different direction, called Rayleigh. Single electron interacting with a single photon or a single atom interacting with a single photon from the outside are the same thing. They're both coherent scatter. They just have different names for the different versions. Okay, so Thomson interactions are a form of coherent scatter dealing with X-ray photon interaction with a single electron. Rayleigh is a form of coherent scatter dealing with the atom as a whole. Yeah?
I think
Wait, go one more time.
X-rays doesn't occur in the natural world.
Oh no, X-rays occur all the time in nature. There's X-rays being produced by particles from the sun smashing into Earth's atmosphere. I might have said something like we produce X-rays artificially, right? So in order to do it in the X-ray room, we have to do it artificially. But nature does these things all the time. It's just far away from us, right? Now there are you stick out your hand. Some X-rays from the atmosphere are passing through your hand. You are being exposed to some of them. Just a very low amount of them. Same with like gamma radiation and stuff like that. It's just that in order to make them in the X-ray room, we have to do it artificially. It might be more closer to what I said. Good. All right. Is the atom ionized in coherent scattering? No. In order for an atom to be ionized, what has to happen? Emmanuel? The electron has to be ejected from the atom. In order for the electron to get ejected, the incoming photon has to have more energy than the electron is bound with, that it's held into the atom with, right? In this type of interaction, we're saying by construction, we're saying the photon has less energy than the binding energy for the electron orbiting the atom. So the atom cannot get ionized here. So we have three types of interactions. Here's a question. Of the three interactions discussed, photoelectric effect, Compton, and coherent scatter, which two result in the ionized atom? Photoelectric and Compton. There you go. Photoelectric and Compton interactions result in that taking place. Okay, good. You guys are doing really good. We have a little bit more to get through, and I got a half an hour left. I'll see how much I can get through in my half hour. Let me pause here.